students. Looks like we have some former students and some presenters.
So actually, I know where the students are in the back row. I have my own rule, and that is to sit near the door and have a fast car outside to say that the lecture's not so interesting. Actually, I have a daughter who will be starting here at Stanford next fall. She applied in early admissions and made it. You know, Grace talked a lot about me, and it's true. I know how to make great designs, and make great designs by accumulating great people. There's no single person that can pull off all of these wonderful projects. It really takes a lot of people who are hardworking and talented and bring some special quality to bear on a project. And if I have a talent, it's maybe as a kind of facilitator in getting people to think about different ways of approaching structural engineering and architecture. So, initially, Greg asked me if I would talk about the development of the structural engineering profession, and I agreed to do that. And then I just sort of ran out of steam. I have a lot on my plate, and so instead I'm going to show you something about the World Trade Center. But just in case you think that's all we do, this is a project we're now doing in Shanghai. It will be the next tallest building in the world, 500 meters to here. And we're in fact, the fourth structural engineering project. And the trick is to take a project that was supposed to be this high and smaller in plan area and put it on foundations that are already constructed. So we put a new kind of structure inside it, which in concept looks something like this. There's a concrete services floor, and it's a brace system, and it's entirely column-free in this area. So the goal here, of course, is to make money for the developer. That's why people build buildings. They don't build buildings to make you feel good or we feel good. They build buildings to make money. So we try to make money for developers and contractors and other people. The World Trade Center, for us, started in 1962. The architect, Minoru Yamasaki, received a commission to design the project. We had been working with Yama largely because of the talents of one of the partners in the firm, Jack Christensen, who produced a fantastic design in our first venture with Yama. So we got this project not because of Jack or because of me, but because neither one of us could have done it. So because of John Skilling, who's one of these persons who has the golden tongue and a real entrepreneur type. And so he was the one who actually made the pitch which got us the project. So what is there about the Trade Center that's unusual? It has what we call a tubular framing system. People say, well, who invented the tubular framing system? And frankly, I don't know. I always blame it on Yamasaki, and he always blamed it on me, and I always blamed it on Fazzer Khan. So somebody did it, I'm sure. It's called an outrigger system. It was the first project put together for which has a linkage between the services core and the lateral core system, which in this case is in the outside wall, kind of giant space ring. And it was really neat because we had designed it but not actually included it in the contract. In structural engineering, it's good to have a back door. There's this thing don't work. What are you going to do? So the space ring was part of our back door. And then the decision was made after all the steel was fabricated to put a 440-foot high tower on top of this building and another one perhaps later on top of that one. So the space ring, of course, solved that problem immediately. We did prefabrication of structural steel to an extent that has never been done before or since. We took a technology developed by two brilliant Danish engineers, Jensen and Frank, who had looked at wind loads on farm structures, on barns, in the full scale, and then they put replicas in the wind tunnel and tried to make them match, and they didn't. That is, in the wind tunnel, they got a downward push on the roof, and in the real building, they got an upward push. We all know that's the case. And so they came up with the idea, what's called a boundary layer wind tunnel, that is to create in the wind tunnel the turbulence of the natural environment. And then in order to decide how much the buildings could move, you have to understand that the World Trade Center was the first high-rise project in which anyone ever thought that it did in fact move. So we built, in fact, 2 different motion simulators to find out how people would respond to the kind of motion of a tall building. I interviewed a lot of psychologists, and they say, what are you worried about? People riding in cars and ships and planes. With building's just another kind of motion, they'll accommodate. Well, the World Trade Center is a $1 billion project when it was constructed, so you don't invest $1 billion without being very sure. I went and rode motion simulators, and I have to tell you, if you ever get a chance to ride a motion simulator to use it in the space industry, don't. And then, in order to deal with the structure motion, we came up with the idea of a damping system. We looked at lots of different kinds, but eventually chose a viscoelastic damping system. We developed a theory for taking the statistical nature of the dynamic pressures from the wind on the glass, as opposed to the statistical nature of the strength of glass, and put them together to try to determine the breakage rate of glass itself in the building. And in buildings at that time, all the walls inside the building were made of block masonry, and they leaked a lot, and they were very expensive to maintain. And so we developed again a theory for stack action. That's large buildings, kind of like a chimney. Cold air outside, the air rushes in at the bottom, rises up through the building, and goes out at the top. So we worked out a system that evaluated that so that we could design for the need of those pressures. And then it was, I think, probably the first and maybe the last high-rise building or craft outside of the military and the atomic energy industry, first designed to resist the impact of a jet aircraft. In this case, the 707 intercontinental version, which was the largest aircraft of its time. We thought it was lost in the fog headed for JFK or elsewhere, similar to the Mitchell bomber that struck the Empire State Building. And we came up with a new kind of partition system that is airtight, allows for building motion, and completely changed the dynamics of a high-rise building, but is now the standard partition used in high-rise buildings around the world. And then we developed a technique for ordering and producing the shop drawings from digital format material to an extent that has not been equal since. And this is Yamasaki. Probably some of you read that he was afraid of heights, that he had these narrow windows. Yama was not afraid of anything. Nothing on his planet that fazed him. I mean, he was maybe a little insecure with heights, but he's definitely not afraid of heights. So the structure has a 60-foot clear span on two sides and a 35-foot clear span on the other. And one thing to notice is that the columns in this direction are very long and hence very strong. They're box columns, very big box columns. And in this direction, there are lots more columns that you strike a line through, but they're, if you will, in a weak axis, so they're much less strong. This is a computer that we use, or a tiny piece of it. Now this washing machine down here was one of the 5 disk drives that we had. Each one had like a long playing record, except it had 7, I think, records inside. This is called the IBM 1620. It was their first solid-state medium-scale computer. We called it Cadet, which meant can't add, didn't even try, because 4 plus 7 by looking it up in a table. So this is the site. It was the site of what was called the electronics industry. Electronics meant vacuum tube. So if you had a radio, it was a vacuum tube radio, and you went down here to get the real cheap stuff. And a lot of controversy over moving all these businesses out of that space. A lot of controversy. But they were well compensated for it, of course, but I don't think you can really ever get compensated by when you're upended. And this whole district disappeared out of New York. There was no replacement for it. So there was no place you could go. Instead, there was a store here and one over there and someplace else. Now we surmised, we didn't know, but we surmised that in the wind, if the wind blows, say in this direction, that the building would lean more or less downwind, not directly downwind, but more or less downwind, and then would oscillate about someplace. This was This came from experience that I had in working on offshore structures. I knew that that was kind of what they did, and I thought, well, a high-rise building might just do the same thing. You have to understand the dynamics of high-rise buildings in the wind did not exist as a subject at that time. But this is a view of Lower Manhattan, and you can see that the wind coming from the south headed up towards the northwest goes over all these high-rise buildings. It becomes very turbulent. Whereas the wind which is coming from this direction is over the water, it's very smooth. And so we designed for these two circumstances using this wonderful idea of Jensen and Frank. And here you see the wind tunnel model. And remember, this is a $1 billion project. So put a big tower on top of this building, the telephone company building, put an anemometer on it, another anemometer on top of this spire, and down on another tower on top of the New York Athletic Club, and we measured in the full scale the turbulence of the wind over the city. And then we replicated it in the wind tunnel, and sure enough, it replicated. So it gave us a lot of confidence that where we were going was kind of sensible. Remember, it's $1 billion, so, and I was 34 years old, so. So here you see an example. This was anemometer, which was on the telephone company building, now called the Verizon building. And you guys can see it, anemometer on top of that spire. The shaft wall partition system was wonderful because it was designed specifically to allow the structure to move without restraining it. And allowed the structure to move and still stay airtight. And arrived at the idea because I rode on top of a lot of elevators in New York City. And well, I went through all the buildings I could. Remember, the tallest building I'd worked on was 22 stories. So I thought maybe people who worked in New York might know something more that I didn't know, which for sure they did. So I decided the partitions, the basic partition system, were terrible, and sat down and came up with this concept, which was then developed by U.S. Gypsum. We did a complete structural analysis of the Empire State Building. This is a trace taken off of from accelerometers, taken off of the building. You see it's very almost random. No kind of neat oscillation can be found there. The only way you can come up with a period of vibration is to drop all these data into a computer and analyze it, and it tells you that it's around 10 seconds, which you can't measure here. So, hey, that's a 10-second period building. No way. So, entirely different. And what was it about the building? The Empire State Building was designed for no wind load at all for the first 100 feet, and then 20 pounds a square foot above that. And we were designing the World Trade Center for something in excess of 100 pounds a square foot. So you'd think that the Empire State Building would have collapsed, or we were wrong. But we did a structural analysis of the Empire State Building frame, and we found that we could, of course, develop the stiffness of the frame, so we knew just how it would deflect under a given lateral load. And then by putting this kind of data from accelerometers and knowing the density, it's possible to experimentally determine the stiffness of the building. And we found that the difference was a factor of 5. That is, the building was 5 times stiffer than the steel frame. And all that came from the infill action of the masonry of the building, and we were designing a building without any masonry. The Trade Center trace looks something like this. You see it's a really neat oscillator. And then the motion simulators, all kinds. We built one which is pendulum. This is the first one. Now, motion in a high-rise building is not a good subject, particularly since no one had ever worried about it before. So we went as far away from New York as possible in a little town in Oregon and built this simulator. And tested people who had no idea what was going on. It was very carefully disguised, so you went into the simulator without, you didn't see any of this junk. You walked from a very nice little office into the simulator. We tested people who had no idea what was going on, gave a little eye test, and then we would start the platform moving and wait to see what happens. We had other people who were told that it was a motion experiment. Some people we retested, who had been tested months before. We had one man who was told nothing, and you have to understand it's a little town in Oregon, and little buildings do not move in little towns of Oregon. They just don't do that. He was actually holding onto the walls. He would not respond to the fact that there was a problem. He was holding onto the walls, people falling over it, because we could get this thing really moving. And then the dampers, very simple devices. They're about a meter long, 3 feet long, and made of viscoelastic material, which in itself is a long story. This is a load deflection diagram for a damper, as you probably all look through the structural field or electrical field would know. The area underneath this curve is the energy consumed in the device. And here you see one of them actually in the building. Am I speaking loudly enough? In the back? Yes. Okay. Thank you. And then a glass. This is the glass is very narrow and very tall. And here you see the deflected shape of the glass. In this case, it's deflecting about 4 inches. And there was no data available on glass of this aspect ratio, that is long and skinny. Those of you who are structural engineers know that the strength is not really related to the span, it's more related to the area of the glass. But anyway, we tested lots and lots of panes of glass to find out how strong it really was, and also to determine what kind of glass to use. And ultimately, it's a semi-tempered glass went into the project. And interesting enough, about half the breakage of the glass has been due to bullets. That is, people from far away, they get a rifle out and they lob bullets for fun, I guess. And at the lobby level, one guy was going by in a pickup truck, and he had a slingshot with 1-inch diameter steel balls, and he would shoot it at the glass, and each time he was successful in breaking one, it was $15,000. So here you see prefabrication. This is the bottom, this is the man, of course, the bottom of the piece, and this is the top. So these are big, big panels. These were prefabricated, and these were prefabricated, and the guys that go on top of that. The floor system was prefabricated. Everything was prefabricated. Here you see in fabrication, now the length and width, the grade of steel, the welding that went into it, everything was provided to the contractor in a punch card format. Those of you who are very ancient like me know what a punch card is. It's about so big, it's got lots of funny little holes in it, and from that you can read data. I don't know when they stopped using them, but probably before you were born.
Still using it for loading.
Oh, I guess that's true. Yeah. Well, we still use FM tape recorders too, but I don't know about that. Here you see some of those panels and coming to the site, ready to be erected up in the project. So it was an enormous logistics operation. So that panel we were talking about was spliced here. This was also prefabricated. When these aluminum panels were being put up, it was February, and the workers said, hey, these things are split, they're cracked. Now, steel was pretty much topped out, and if you don't think having split connections at the bottom is not an interesting subject, it was, of course. So we pushed the panic button and decided that the problem came from water inside and freezing. And again, we went as far from New York as possible. Actually, we went to Berkeley, hired 2 esteemed professors who produced a report a month and a half that took them to do it. They agreed that it was a freezing problem. In the meantime, we had to fix them all, of course, because you can't wait around to report. This is sort of a standard piece. You see this bulge. Now, our client, the Port Authority of New York and New Jersey, was a fantastic client, absolutely incredible client. They never said no on any subject. Well, they could be a little tough sometimes. But this is one instance when they overrode our judgment, and that is they put the control of water inside of the structure in the hands of the contractor. And our policy is steel plates on all box sections so that you cannot get water inside for this very reason. Indeed, that night, some 85 pipe columns broke on the split on the adjacent small buildings that are under construction. These box columns were used for everything. If you had a hose and water running out of it, you didn't put it down. You just put it in the box column because then it didn't get people wet below. So there was water everywhere. We took out of some of these columns 600 gallons of water. And then billion-dollar project, let's not forget, after it was all done, got a completely new team, went down, looked for water, and found it. So, very big problem with water inside of college structures. But anyway, we've got rid of all of it. It's a prefabricated wall panel. There were thousands of these manufactured. And the steel, all the steel plate came from Japan, so punch cards. No way to send them across except by airplane. Today we wouldn't bother, but so this plate and this plate and so forth, all of these were fabricated in Japan. In the United States, the steel industry was in the mood of, well, this is what we make, how can you use it? In Japan, there were, what is it that we could make that you could use? So we bought steel for the project in increments of 5 psi, which is fantastic, of course, for the overall toughness of the building. Really fantastic. So we didn't have over-yield material in the project. These were fabricated in the state of Washington. And this is a readout of punch cards. Now, Port Authority legal department said, okay, well, this is the basis of the contract. And we said, no, it's got to be the punch card. No, they said it had to be this one. And of course, the legal department won. But ultimately they did. The contractors came back and said, hey, we saved all this data and we wanted it in the punch cards, and then we don't want to use these at all. We just want to have the cards. That should be the basis of the contract. And ultimately, they relented. The legal department relented. They were assembled something like this, a spandrel plate, a big broad plate, and the interface of the column plate was welded together, butt welded together. And then this shown in blue, another assembly with the stiffener plate inside was then added to it, and an outside wet plate was added last. Notice that there's no weld between the stiffener and the outside wet plate. Today, it'd be just like that. I mean, you pop this into your favorite finite element program, and out would come an answer. But at that time, that technology was not available, and so we did most of the finite element work based on very big programs, but not suitable for actual practical work. So we did a lot of finite element work on the World Trade Center. This kind of example also is physical testing, of course. So the way it was put together, like this: first the bed sheet, as well as the flat plate, then the stiffener and the flange plate, and finally the wet plate on top. And it was done with such precision that it was possible to maintain a very tight tolerance between the architectural work and the structural work. And normally we would allow in here about 2 inches, that is 4 inches at the very least. But since our columns were 14 inches, that 4 inches was a big number. Here you see them in fabrication. This is that sort of bed sheet, fabricated first. It was, in my experience, the first time that steel fabrication was done with the material moving by the workman rather than the workman going to the steelwork, i.e. Leaning back on the technology, I guess, first popularized by Henry Ford. Then assembled into big panels. Then these went into a jig, and the ends of the 3 columns were all milled in the jig without moving it. All the bolt holes were drilled in the panel, again without moving it. So we were able to maintain very, very tight tolerances in these panels. They went together sort of like a Lego set. It was fantastic. They just went up no problem. To put them together, there were 2 holes, a large hole above at the bottom of the column and a smaller one at the top of the column. Basically put the impact wrench for tensioning the bolts right inside the column and tension the bolts. Floor system was prefabricated. In this case, this panel 60 feet long, 20 feet wide. Metal deck was already in place. Electrical distribution cells already in place. So when you put one down, you created quite a significant space, 1,200 square feet. Here you see a panel in the air. There was one attempt to bring these over by helicopter. These, of course, weigh almost nothing. They're just mostly air. And the pilot got over New York Harbor and decided that he wasn't going to risk his life to carry it any farther. So sometime if you're out scuba diving in New York Harbor, you'll find the associate architect firm no longer in business, decided that it was important to have large openings in through the facade. And remember, these columns are 4 inches on center. So they asked that we maintain big openings. So this, a large opening, and then diagonally across the building, oops, this way, sorry, there's another opening just like it. And then go down the side, you have this one. So the openings are diagonally opposite each other like this, so that at no one level do they cross the complete building. But they were never used. Great idea, like a lot of great ideas, didn't find fruition. So here you see there's something about the whole assembly. The prefabricated wall panel, prefabricated floor panels, and so forth. Not shown as a damper because they were put in later. The floor system, been a lot of in the press about the floor system being very vulnerable to all sorts of things, but in fact it was designed so that you could remove, depending on where you were, 2, 3, 4, 5, sometimes 8 of these trusses, and the whole system remained stable. It was a grillage, as you can see here, a grillage of trusses, not just a one-way system. Very, very sturdy system. And a lot of talk about the connection of these trusses to the outside wall. The normal criteria used by structural engineers is that the connection to keep a column from falling off the building, if you will, is you use 2% of the axial load in the column. That's a good rule of thumb. So this is 2%, and this shows the actual connection capacity that was built into those spaces. So if you take the North Tower, it was designed for something like 15 or 18 times more than what you would consider standard criteria. Here you see something about an important aspect of Trade Center, and that is not a single iron worker lost his life on the project. And that in no small measure because of this jail-like exterior of the building. Notice that the panels are spliced, only 1/3 of them in any given level. As this is a splice, up one floor, another one, up one floor, another. So that there were no column splices in 2/3 of the columns in any given level, which again provided for toughness and redundancy in the structural design. So the jail-like nature of the outside wall, the prefabrication of the floor system, which made it pretty hard to fall through, and the use of shaft wall, which allows the metal studs to go up around the openings in the services core prior to the installation of the sheetrock. And so it really worked. Oh, add to that a wonderful safety program on the part of our great client, Port Authority of New York, and New Jersey. They did a great job. These aerial pictures I do not take. The rest of it is pretty much my photography. So you can see the good ones. This is somebody else. To get a sense of the very high aspect ratio of the cameras. This landfill was created from the World Trade Center, and then a lot of landfill was added later to create Battery Park City, a huge development in Lower Manhattan. People talk about iron workers, the construction workers being lazy and all that, but that's not my experience. These guys work really hard. And this is the roof of the 440-foot tower that went on top of the Trade Center. It was fabricated by Montague Betts, but as far as I can see, learned how to fabricate steel in this project. But we had 3 engineers full-time in their shop. And then there was the great day of the topping out ceremony. Here you see, well, it wasn't the last piece of steel, but the symbolic last piece of steel going up. I took this picture and then went inside, rode an elevator up, transferred, rode another elevator up, climbed a bunch of ladders and stairs, and finally got to the top, and this is what I saw. It was cold, and it was foggy. And nobody knew where this piece of steel was. But I did, because I had been down on the ground. So I explained to the assembled throng where it was. I started out across the steelwork. In this case, it's the roof of the building. There's no prefabricated steelwork. And it was foggy. And it was cold. And the steel was icy. And let me tell you, it was really slippery. And I was walking very carefully. I have a yellow streak up my back. But anyway, I got about halfway across the second beam, and I just stopped. I just I didn't know what the problem was, but anyway, I stopped, started to turn around and go back. No, I started forward again. Again, I stopped. And then I did turn around, and behind me were these TV crews. They were walking across the street like this. Like it was nothing. You know, of course, when you have that kind of people behind you, you gain a new courage, or maybe you're too ashamed to show your fear. This is the way the TV camera went over this from the Empire State Building to the World Trade Center, but I assure you that's not what happened. But Philippe Petit, a wonderful man, talked about his crossing between the two towers. In fact, he didn't just cross; he actually performed. It was quite an event, and we became good friends later, and we've done several bits for him. But here you see him. And what he didn't know, until I explained it to him, that these buildings oscillate in the wind. They don't do this way so that the cable stays nice and straight, but they do this kind of thing. So he was fortunate that no wind came up, and he's alive today and still performing. Great guy. Anyway, we finished it. And felt pretty good about it, actually. And then came 1993, and a bomb went off shortly after noon. We discovered that the bomb had gone off because we had 4 police cars out in front of our offices. Had to take engineers down to the site. So we went down there. Actually, I wasn't there. I was at my house in Connecticut. But discovered from the television that there was this problem in Coleman. Yes. So drove into the city, and the bomb went off sorry, I'm just coming from Metric World, about 6 feet from Tower 1, and right in this area, right here. The bomb was about the same size as the one that took down the structure at Oklahoma City, almost identical in terms of the capacity. But what happened was this steel wall, if you will, very, very heavy and robust. It just reflected most of the energy of the bomb to the south. Blew a huge hole through the B1 level, and then caused structural damage about 350 feet was into the south. Still significant structural damage. But the bombers, I think, were trying to bring down the World Trade Center to make it collapse. But the most important thing that they did was they destroyed the airlock around the building. Remember I talked about stack action? Well, when you go through the revolving doors of a high-rise building, you're going through an airlock. That's to prevent the air from rushing into the building and upward, consuming a lot of energy and other things. So when the bomb went off, it created a huge hole at the base of the building, and the pressure distribution went from something like this to something like this, and all of the smoke and soot and so forth from the bomb area immediately rose up inside of the towers. And you saw photographs, I'm sure, of people coming out of spaces and clothes totally covered with soot, and great human suffering from that event. That was the worst thing that happened with respect to the bombing. The next thing that happened was all of the debris from the collapsed areas of concrete work fell on top of the refrigeration plant. Now it's just a refrigeration plant, you build a new one. But the problem with the refrigeration plant is that if it couldn't be got into operation by June, you'd shut down the World Trade Center because there's no operable sash, no air conditioning, you cannot work in the building. So Port Authority built a temporary refrigeration plant outside. Now the day of the bombing, or the night of the bombing, just before midnight, 4 of us went down to the basement to look at the refrigeration equipment because I want to know what was underneath all the debris. I knew it was there. It was the refrigeration equipment. But 4 was too many people. We had our flashlights were too small. So the next morning, I had a couple hours sleep. I went down by myself and looked at the refrigeration equipment. These pressure vessels were designed to pump water from the top of the World Trade Center. These are not, pieces of sheet metal or something. And they looked in pretty good shape to me. But Port Authority still went ahead and built these plants, which were never used. We brought people out of retirement. The average person in the office worked for 90 hours each week. We served breakfast, lunch, and dinner in the office, working for breakfast, lunch, and dinner. These were working meals. The devastation was pretty bad, and these columns were supporting a hotel. And those of you who know about columns realize we designed them with lateral supports, and when you take the lateral support away, there's the prospect of buckling. So it was a mess. Remember all this heavy stuff sitting on top of the refrigeration. And so these columns were actually braced. They were fixed-ended, if you will, by being buried in this mound of debris. But, you know, it's hard to calculate the lateral support from debris. So that night, Friday night, I worked on braced these columns. This morning, made the sketch, had the fabricator into our office at noon time. They agreed this was a good way to do it. It looks pretty neat, right? Yeah. The reality was not quite so nice, but it worked. I mean, you know, it was possible to do this really fast. We thought that we could start on Sunday, and the steel was delivered on Sunday, but this was a crime scene, and we had a sort of a summit meeting because there were 5 different police jurisdictions. We had a summit meeting about every 3rd day because someone there would say, well, you can't go into that part of the work. And our response was very straightforward. You can't go there either because we controlled where in the project people could go. So we had this sort of a standoff every 3rd day. But on Monday, we were able to get a hole through the floor and start lowering people down. In fact, this photograph was took from a kind of bosun's chair, dropped down through a small hole into the middle of this great abyss. So this was the situation. Refrigeration equipment down here, a lot of rubble piled on top of it. And one of the exciting things is that this support, which was really critical to this the slurry wall, which keeps out the Hudson River, was working because the slabs dangled down into the debris. So it was the concrete structure holding up the refrigeration equipment, holding up the debris, holding up the collapsed slab, which was in fact keeping out the Hudson River. So the whole logistics of take out this, do this, over it, represented thousands of drawings that we produced in our office. And much of the work we did was just that. It was not so much designing things, as it was sorting out what could be done in terms of the actual operation itself. Those of you who know about shock waves, these are drop panels, and there's a picture. Drop panels for a flat slab system. The pressure wave would come this way and hit the forward edge of the drop panel. I'd pretty much leave it there, no big deal. But get to the leeward side, and the shock wave going on, it would put the concrete in tension and ripped off most of the back sides of the drop panels for about 200 feet. This exciting structure is there because there was a big fire some 5 years earlier, and rather than try to evaluate the quality to reinforce these steel and so forth, we just bolstered the slabs with these elegant devices. Much of the repair was like this. It's just knock out the concrete, which was all cracked and broken, jack up the slabs, and reconcrete it. Now the bomb went off 6 feet out this way from here. There was a diagonal brace here, and this one, and a column. This diagonal brace is made like a T-section with bolted together in the center of the web. And if you look at the picture carefully, you see the flange of the T goes right by the column. Doesn't intersect the column, but goes right by it, and it's a kind of an applique. And the detail works extremely well because these columns are not exactly where they're supposed to be. They're always out of position. They're twisted a little bit, and so forth. So this detail allowed us to carry very heavy loads through the system without having actually connected to the column itself for large forces. Anyway, this brace went inside, killed 2 people. The outside piece fell into the into the hole and was never found. It just got carried out with the debris. And the other one, here you see a view looking at the other one. You see this big crack here. This took place, of course, because of the impact loading. You can't do this in a testing machine. You've got to like hit it with a giant hammer. This piece, no one knows where it went. It's a spiritual place. And this one was hidden by the ironworkers because I admired it, and I stuck it off in the corner where the Port Authority couldn't find it, and then later on they took it out to my house. Here you see it when it was first erected. So there were lots of cars. The place was full of automobiles. This slab used to be up here. I took lots of pictures of automobiles because imagine if you had an automobile in this space. Wouldn't it be great to have a picture of it? Well, I took pictures, particularly if I did license plates. I took photographs of the automobiles and sent them to the people who owned the cars. There's hundreds of them thank you letters. Wherever there was structural steel around, the concrete suffered more. There was, all of the telephone conduits from Lower Manhattan went to the telephone company building through the basement of the World Trade Center. This is a tiny fraction of it. So we put a team to work around midnight, and at 9 o'clock in the morning we went down with the drawings of how to hoist all this conduit back up, get it off of the cars, because you had to remove the cars before you could get to the structure, and you had to inspect the cars because that's what police do. Anyway, interesting enough, not a single wire was broken in the operation. I blame that on the contractor who was being too careful. We had all these, this is a terrible picture, but these bomb squads, this is a bomb squad, they were out there with dustpans and whisk brooms going through the rubble looking for pieces. Later on, I testified for 2 days in the trial of the 5 who were convicted of this matter, and these people picked up incredibly small pieces of that van. Unbelievable. Big pieces, little pieces. They had almost the whole van. So every time you got near structural steel, the concrete broke up very badly because it could not deflect away from the pressure wave. Remember, this is not a static loading that's taking place here. It's a more or less instantaneous loading. Anyway, it was finished and this memorial was built. I always hated the memorial legend. It was built, and again, we sort of went back to sleep and forgot about the location. And then Minoru Yamasaki came down with cancer, and he was in Sloan Center, which is a famous hospital in New York City. I went to see him every day. And he wanted me to look after the Trade Center. And not only that, he wanted me to make sure that the young engineers would continue to look after the Trade Center. Anyway, then this is it. This photograph was taken from our offices. If you saw the slow motion videos where they were just looking at images one at a time, you discovered that the whole airplane disappeared into the south facade and could not be seen, and then the great fireball erupted. So this is the north face of the North Tower, and you see that a very substantial amount of structure was removed, and yet the structure above was able to span over this huge opening without, seemingly without stress. This is a sort of blow-up that took place. Okay, a lot of you know about energy and impulse and momentum and all those things, and I don't want to have a big discussion here on that subject. How much of the energy went into crumpling the airplane, and how much it went into ruining the buildings, and how much it went through and came out the other side. This is just to give you scale. The Mitchell bomber that hit the Empire State Building had this much energy. It's just a little mark here. We designed for the 707, but it was more or less fuel-empty 707 because it was a landing 707, and it was lost in the fog, so obviously they didn't have the hammer down on the throttle. And this is, in fact, the kinetic energy of the aircraft that struck the building. So you see it was many times larger than the design criteria. The fire safety issues in the building were not our responsibility, although, you know, we dabbled in most everything. But in any event, I don't think anyone knew how to, I don't think anyone knew what happened when you crashed a 707. All those tests were done later. But in any event, this is the amount of fuel that was in the Mitchell bomber, and this is the 707. This is what we designed for. And this is what was in the 767s that hit the aircraft. And again, this is not a good comparison, but the bomb that at Oklahoma City, which is pretty well documented, even the one at the Trade Center, about 200 liters of fuel compared to 45,000, 46,000 in the 767. So you see a huge difference in the amount of energy released. And now we go, that's, if you will, the kind of good news. The bad news now comes forward. This is just an idea what that V-25 would look like. It's just about to get. This is our 707. It's a 767. It's the 747, which is actually wind spread a little bit bigger than the floor space. And this is the new Airbus. And now, in kinetic energy, we can't get the Mitchell bomber because it's too small in terms of the amount of energy released. But this is the 747 as compared to the 767, and this is the new Airbus. In terms of fuel, not so startling, but still, when you think of what happened to the Trade Center with the not quite 2 tons of TNT, which is about 200 liters of fuel, compared to the over 300,000 liters that comes with the new Airbus. You realize that it's not practical or sensible. I mean, you can design anything for anything, I guess, but you can't design buildings that you or I would ever want to live or work in for this kind of circumstance. Totally out of the question. And engineers have written saying, well, you know, it's patently ridiculous if the project wasn't designed to take the impact of the aircraft. And I understand what's in their minds. You could land a 767 inside of the World Trade Center. It would look like this. This is the North Tower. Remember, the plane is traveling in this direction, the strong axis of the columns. And in the South Tower, in this direction, we're going in the weak axis of the columns. And then this is the time temperature curve. This is standard ASTM time temperature curve for a fire in a building. And this just took it out of the petrochemical industry, offshore structures generally. What happens if you have a petrochemical fire? So you see, it's very different. People said, well, you should use concrete fireproofing, and this shows you something about the strength versus temperature of concrete versus steel, and you see there's not all that much difference. What happens when you put this high energy on the concrete, it sort of just goes off like the popcorn. It just flies away. Indeed, if you look at the columns of the Pentagon, which were square with a round cage of reinforcing inside, after the impact, the columns were round. That is, all of the outside concrete gone. So the steel was, the reinforcing steel was then exposed. Okay, this is the area that was at least partly damaged because of the circumstances of the last of September. To give you an idea of the cost, some of this is estimated, but in the World Trade Center attack, this is going backwards because you're guessing, and about $50 billion. Hurricane Andrew, the largest to date, almost $20 billion. The Northridge earthquake, almost $15 billion. Most of the big catastrophic events are associated with windstorms. the project looks something like this. The North Tower, called Tower 1, South Tower, Tower 2, the hotel, Building 3, you should memorize these numbers. This is Building 4, 5, 6, and then across the street is Building 7. Now, we were not the engineers for Building 7, so I'm not going to talk about that. I'll show you some pictures. We did the base of the hotel, but other engineers did the superstructure on top of it. So this is Building 4. You see a piece of the, or part of the North Tower fell down and just wiped off the corner of the building. Just gone completely. If you go between Buildings 4 and 5, you see some of these wall panels. You recognize the 3 columns wide. Fell down and the building was able to support them. You see these pipe columns are all bent and buckled and so forth. That's mostly from the fire that took place. Fortunately, the structure was very redundant. There's a moment frame that goes back into the building and then the columns on the outside. And there was a load distribution between the two so that you could take out columns or take out frames and still it wouldn't fall down. There was a huge sculpture piece in the middle of the plaza. It's another thing I've always hated. You won't believe it. We designed the crate that this thing came in. I sent an engineer to Germany to supervise the crating. It was that expensive. I came here, and then after the event, it looked like this. So it did pretty well. This is the east wall of the north. The east wall of the North Tower. This is part of the services core of the North Tower. Looking at what was the South Tower. You can see it was not a real safe place to work. All kinds of things hammering out and rooted in who knew what. And this wall panel was spliced up here someplace. And nobody knew the condition of the bolts, but still people were working through the area. Because at this time, this photograph was on Sunday following the event. I was in Hong Kong when it took place, so with good help with the government of the state of New York, I was able to get back to New York really fast. But it was Sunday when I took these photographs. So the firemen were out there. The project burned for about 2 months and even later than that. But the firemen and the policemen were out there. They weren't worried about the fire. They just let the buildings burn. They were concerned, of course, about the people. So this is Building 5. You can see that this is a piece of the tower which failed inside, and rigid frame going inside, buckled columns, and the great tower. Where really heavy structure came down and would just wipe out the building. So you see here a whole bunch of structure fell and just took out the, in this case, the south face of Tower 5. Our people, the respirators were mandatory. We didn't let people go out on the site without them. There was huge asbestos abatement program that was there, but so almost all of it was gone, and there were regular monitoring in the air. The Port Authority was fantastic about things like that. But still, it was extremely dusty. We have the 47th and 48th floor building looked down onto the site, and we just taped up all the windows because it keeps the dust out. That's Building 7, which is just to the north of the project. And people have asked me about this pile of dirt. Why is there a pile of dirt in the building? Of course, concrete is made out of sand and gravel, and when you pulverize it, you get back sand and gravel, which looks like dirt. So this is really pulverized concrete, which you're looking at. You see it everywhere. This is, again, next to Building 7. This building stood up pretty well, suffered a little damage. This Building 7 collapsed right through here. Here you see one of the transfer girders from Building 7. And this is the Verizon building, the telephone company building, part of the transfer system. We got left in place when it collapsed. This building burned 6 or 8 hours and then collapsed at the end of the day. And will be the subject of intense scrutiny because I believe it's the only major building, 47 stories, the only major building that's ever collapsed in a fire, just with no other reason. The towers, of course, collapsed, but they had aircraft impacts, fires, and other nasty things, but this building collapsed just because of the fire, so it's very, very worrisome to us. This is right across the street from Building 7. This is Building 6, and you see again where the debris is fallen. American Express building, and this is again a piece of steel from the North Tower, and went there to look at what took place. No structural damage or consequence in the building, but all of the fireproofing in this area was removed by this event, and it was, I suppose, just the impact and the vibration of the steelwork that shook off the fireproofing. So there's a lot of talk about maybe more robust fireproofing systems. I don't know. I'm not a believer in designing buildings for aircraft impact, so I'm not advocating spending a lot of money to make that possible. That's the Winter Garden, designed by the architect R.L.P, led into Battery Park City. And this end of it was pretty badly damaged. This used to be a bridge across the street. The other end, however, was in impeccable condition. Very dirty, but not damaged at all. So here we look at what was left of the South Tower. This is looking towards the south and east. The photographs were taken, if the National Guard caught you with a camera, they took the film. So sometimes the color balance is a little bad on these pictures because, I was having in my shirt and stuff like that. Really relatively superficial damage to the buildings across the street, but still months before these buildings will be in operation. Now, this structure is in some ways, strangely beautiful. We had it, when the bombing in '93, we hired an architect and his wife to assist us in some areas, and he stayed on work for us until 3 years ago. His wife's still in our employ, and they were having coffee on the 80th floor of the 90s of the North Tower in the plane deck. So she walked out. This is a bucket brigade. These people are taking debris out of here and passing it back and dumping it in order to look for people. Extraordinary dangerous work. All this we remember now is the Sunday after the fact. Actually, this was the sort of regular path that everyone went through. We looked up and saw this kind of stuff. It's inside of Building 6. Steelwork came down and sort of created an atrium inside the building. This is Building 3, the hotel. And the executives from the Port Authority left the North Tower following the impact. They were all located in the high 40s. They walked out, and they collected in the lobby of the Vista Hotel. It's the Marriott Hotel, I guess. Changed the Marriott Hotel. They were in this building when it collapsed on top of them. And they all survived. We had put in a transfer girder at this level, which somehow arrested the collapse. Inside the core of the connections, we call them semi-rigid. They were designed to stabilize the columns from buckling, so they It was a kind of like a rigid frame, but with lots of eccentricity. But you could see the welds did pretty good. They behaved as well as one could expect, I think. It's a typical column splice. You saw this everywhere. This is one of those 3 column-wide panels. This is the inside face of the building. This is the outside face. And clearly, because it was so common, the panel tipped out of the building, and as it tipped out, these bolts, of course, went into high tension and failed. And when you stuck your hand inside it, you could find the bolts, which is not easy because often they were way up inside the column. Classical tension failure in the bolts. The ones on the outside face, because it was rotating, they bent over and then cracked. So you saw this combination, very common. These connections were made with either 4 or 6 bolts and either 325 or 490 volts. This kind of column was low in the building in the services floor. You see this 4-inch thick plate, and either hit something or was hit by something and fell. Not due to some aircraft, but it's due to the building collapsing. The hotel was here. This is South Tower. Here you see one of those prefabricated elements now dangling off of the construction. There's no support. Those of you who are not in the construction business might not understand this red stuff on the outside. If you're ever around a high-rise building, you see it's on fire, don't stand there and look at it. Leave. Because the fire causes the glass to break. When the glass breaks, it kind of floats down through the air. It can travel long distances horizontally, and it sort of floats, and then it floats, and so forth. So if you get hit by a piece of glass, you might not survive. So this is just to keep the glass from sort of tinkles down inside of the netting and doesn't go outside. Building immediately to the south had some pieces hit it, removed this column completely. This is a big controversy. This is building 6, and they wanted to demolish it by working from west to east. And we said, well, nobody knows how strong that building is now, and it's holding up this steelwork from the north tower. And so demolish this first and then go for the building. They added about 2 weeks onto the demolition time, but I think it was worth it because no one really knew what was happening if you just went ahead and demolished the work. Go down to the basement. Now this is, remember the bomb in 1993? So this is that same construction again. You see the box column, these are 4-inch grade columns. Some of them up to the 80 and 90 yield material. You see, when they tipped, the whole wall tipped over, as you saw in the photograph. Sometimes fracture out large blocks of the steel like this. This steel was not particularly ductile. It wasn't intended to be taking any great lateral force. The lateral force went down through the diagonal system. So there was no intent of there being any bending or anything of that sort in these columns. This building was done by the architect Cass Gilbert. It's a terracotta facade, and it looks now as though it's going to be saved. I know that if it were to be taken down, there would be people lying in the streets. It's a beautiful old building in Lower Manhattan. One of 4 or 5 or 6 buildings done by architect Cass Gilbert. So I used to have this office there. You get around in the basement areas which got about 6 or 8 feet of water almost right away. You went by boat, but it was pretty uncertain as what was down there. This guy is not a scuba diver. We went down with air tanks because of concern about the quality of the air itself, not because of we're going to go diving or something. We noticed that there's no motor. That's the motor in our oars because, again, there was no desire to have sparks or anything burning down there. Because when you were down there, you have to remember, above you, the project was on fire for months. So, we were down at the B1 level, and one of the firefighters said, I think you'd be interested in this, and they pulled off a big block of concrete, and there was like a little river of steel flowing. This is what's left of one part of the TV tower that used to be on the one tower. In fact, this is south of the project. The slurry wall was built with the tieback system. The light lines were the old tiebacks, which were long ago de-stressed, of course, and the new tiebacks were put in place for the dark lines. Pretty conventional system. There have been some scary moments down there with the slurry wall. I'm sure it will never be used in the future as structure. It will just be used as an outside form for the construction of a new wall. The SC FEMA team, or I guess I should say FEMA SC team, in New Jersey, at one of the junkyards, you could see the steel was just piled up in a tangled mess. To the extent the steel has been found, which was near the site or at the site where the plane struck, that steel has been removed. I guess it's going to NIST as a multi-million-dollar contract to look into the issues. There was one professor from another university who had set aside a piece of steel, which he said was from the impact area, and he was very proud of it. It had an aluminum piece of the airplane on it. But I looked at it, and as you can imagine, every piece of steel has a number on it. And you don't just look at it and say, well, I think that might go on the 37th floor. You have to know where it goes. So it was a piece of steel from the 44th floor, which is rather far from the impact area, and the aluminum work was, in fact, part of the facade. Again, fast-forward design. Wonderful architect. And then there are two major churches in Lower Manhattan. Most of you go there, go to Trinity Church, which is at the foot of Wall Street. But if you walk just a little bit north, you come to this lovely, lovely chapel. And following the collapse of the towers, it was in absolutely terrible shape. But terrible shape because it was covered with gravel and soot and cement and paper and pieces of typewriters and computers, but not a single piece of glass was broken. And I suppose this is the last photo, and took this from New Jersey. You're looking right down through the elevator shaft, the corridor walls, I'm sorry. The skin's in place, glass is in place. It's essentially a building that could be occupied. So to give you an idea how light and airy these high-rise buildings really are. So it varies a lot, but somewhere between 7 and 12 pounds a cubic foot is what high-rise buildings weigh compared to steel. So there you have it. I had one thought that maybe a lot of people have talked about these people who ran into the building and how I felt about them, how I feel about them. And I worked a lot in the Muslim world, and I have a lot of respect for them. And I think that somehow the world's gone awry on giving a political opinion, and that is that we've gone into Afghanistan looking for a man who might not even have been there. Now there's talk about going into Iraq or someplace. And I know, I'm totally confident, that this problem of the Muslim world hating us and hating Israel is not going to go away until we deal with the fundamental issue. And once we've made peace with the Muslim world, and I don't know how to do that, I know that's right. is not going to be solved. The problem will be with us for several generations as this hatred somehow goes away. So anyway, if you have questions, I'd be happy to. The original plan for the trade center was to be on the east side of Manhattan, and this is all very political. And then it was moved to the west side of Manhattan in order to bring the state of New Jersey into the act. It was built on the site of the PATH system, Port Authority Trans-Hudson Railroad. There were two large buildings on the site which were demolished for the trade center, which was the station. The original architects had conceived of a kind of a Maginot Line 60-story building on the site. And Yamasaki came up with the idea of two towers to get the required area that was needed. Originally, the plan was like 80-story buildings. We worked on ideas for 80-story buildings, and then it became 100-story buildings, and we worked on ideas for 100-story buildings. And in fact, obtained a commission on the basis of 100-story buildings, and then they became 110-story buildings, all the time to try to get more real estate out of the project. So it was not a decision on the part of lowly people like me. It was done by great people with lots of money. The Rockefellers did it like that.
Size and location of the stairs. Can you comment on that?
Location of stairs.
And the size of the stairs.
Okay. The building code at the time in New York City required in the towers, let's talk about the towers first, required two stairs. The exit widths are established by code. And a decision which I had absolutely nothing to do with, Port Authority decided to put in 3 stairs. And so they added actually 50% onto the total exit width. As you probably understand, at the top of the building, the stairs are narrower. As you go down, they get bigger and bigger and wider, I should say. To the best of my knowledge, and I've talked to a lot of people, to the best of my knowledge, the stairs worked extremely well. Now, part of that was because in the bombing of 1993, a lot of things did not work. First of all, the stairs were full of smoke and soot. Subsequent to that, Port Authority redid all the stairs, put in striping in the stairs to show how to get down, completely redid the audio communication systems, took the central computer, which was outdated, spread it around, brought it up to date, took the emergency generators that were all in one place, spread them around the project, and so forth. And to the best of my knowledge, the stairs worked extremely well. Now, nobody knows what those stairs were like but if you go into the low buildings around the outside, which burned out, and you go to a stair, it's a blackened mess, and you can in fact take the gypsum off with your fingers. But interestingly enough, the doors would open, you could go inside the stair, and it was white, painted white. And occasionally you'd see a little black tail at the top of the shaft wall partition where a little smoke had gotten into the stair. But clearly they worked extremely well. So I presume that in the towers they worked extremely well also, below the impact of it.
I was watching a video on the firemen that were going in, and if I remember correctly, they were predicting it would have taken an hour and a half or to go up the stairs. And I was wondering if that is how...
Okay. In New York City, firemen do not use the elevators. they walk up. Now, some of you are probably pretty good at condition, and you can do that to the top of the Trade Center in a whole lot faster than an hour and a half. But the firemen are carrying a lot of equipment, and they generally go about 3 or 4 floors and they stop and rest. And then they go 3 or 4 more and they stop and rest. And a part of that, I think, is to reduce the incidence of heart attack in firemen. I think it's probably a prudent thing to do. I happen to know, I did it in 27 minutes on the Saturday morning following the 93 bombing. I went up to the top of the building to look at the equipment that measures the swaying motion of the building. There's accelerometers there, and I didn't have the key, so I knocked the door off its hinges and went inside, but the building didn't move enough to trigger the recording system, so there's no recording made. I have no idea the accuracy of the number that you just stated. I wouldn't know. But every year there was a race, of course. I don't know. They did it in 10 minutes or something like that.
I'm not a structural engineer, I'm a AA, but I have read recently that some of the methods used for testing structural components in tall buildings are nearly a century old. Is there progress being made to improve testing techniques?
We're talking about 1902. I don't know that there's a piece of equipment around to test structures that's that old. Do you know of anything that old? Do you have anything at Stanford that's I see, like, they heard that same report. They said, no, I don't think so. I think that's probably not an accurate measure of what's going on.
There's a tension tester at Montana Tech in Butte, Montana.
Just 100 years old? Yeah, okay, well, I mean, there's some things that are pretty fundamental. I mean, the thing that you lift your car up, called a jack, hasn't changed in 100 years. So, they're a fundamental thing. So I don't dispute that there are, but realistically, the equipment that's used today is entirely different and, of course, heavily dependent on your discipline for it. In fact, any good structural engineer who does research becomes an electrical engineer right off the bat. Isn't that right? I mean, you can't maintain the equipment. They don't call your department to fix it.
I'm not an engineer of any kind, so I can't apologize if my question sounds naive. But it appears that not only the walls of the World Trade Center, but every building around there are parallel. If they're parallel, they can't all be vertical. So one wall or some might be vertical, but all can't be vertical. And part B of my question is the floor flat or level?
I must say, I don't understand your question. There are,
If they're vertical, they have to be radians from the earth. So
I see parallel. Oh, you're talking about convergence. Oh, no, actually, the dimension at the top and the dimension at the bottom is exactly the same. They are not, the walls are not perpendicular to the theoretical surface, but I don't know what the convergence is. Anybody know? Somebody got that answer just like that?
About a tenth of a foot or so.
In the height of the building?
Yeah.
Is it that much? I'm surprised it's that much. But anyway, it is what it is. These are square cylinders. They do not taper at all. So they are then not perpendicular to the surface of the earth, if that's what you're saying. Absolutely not. I don't think anyone would recommend going the other way. How about the base? Okay, now level and flat. With this, first of all, there's nothing in structures that is either level or flat or perpendicular or vertical. Everything has a tolerance. So the technique for making the floors of a building, you get out a laser level, and you see the little. I see the little dot running around, except it runs around absolutely level, right? And the floors are screened to that level. So it's then perpendicular to the device, which may or may not be perpendicular to the earth. But I mean, if you get the floor within, let's say half an inch, you're doing pretty good. So I don't think that the fact that it's either parallel or not to the surface of it has any real significance in the building.
I apologize if I missed you talking about this, but what is the foundation?
Foundations here?
Yeah.
Wow, it's fantastic. In concept, the slurry wall went down to what's called mica schist. It's extremely strong rock. And then all the material inside was removed. Well, not all of it, but almost all of it. And the foundations are built right on top of the rock. And it's extremely strong, which has assets and liabilities. The asset is the kind of size of the footings is pretty small. The liability is in softer materials you get a certain amount of damping from the softer materials, which you don't get with this rock, which is very elastic.
Could you describe a little bit more about the procedure that you used to design for the impact of the airplane to the towers?
The question is, how do we design for the impact of the 707? The kind of computer programs that are now available to do that sort of thing were definitely not available at that time. The technique that we used was to make an assumption about a structure that was to be removed, and then we would do a very slow dynamic analysis, right? So increment at a time dynamic analysis of the behavior of the structure of the outside wall. Inside of the services core, basically we took the assumption that the engines, remember these were 707, so they had 4 engines that were rather smaller than the engines of the 767, quite a bit smaller. We just calculated estimated, better way to put it, we estimated the energy required to bend the column out of the way, and then we would subtract that from the velocity energy of the engine and until it stopped. And so we just assumed all those columns were removed. And again, it's sort of very slow dynamic analysis. We had one thing that was very useful, and it's the space frame at the top of the building is really good at sort of holding things up and redistributing the load. So there was not only the horizontal distribution of the outside wall, which is obvious looking at the pictures, but the space frame at the top created the ability to transfer load from the outside to the inside and from the inside to the outside. And if you look at the photographs of the collapse, you get the sense that in the north tower, the core started down first. It certainly looks that way when you look at the photographs, which meant that somehow that whole thing became overloaded and started down. We've looked at it as best we can, and we haven't figured out a way to arrest the collapse of 30 or 40 stories worth of buildings as it starts down. There's no practical structure you can put in there. Once it starts, it's going to go all the way down.
Can you say anything more about the mechanism of collapse of those towers?
No, actually, I can't. First of all, I haven't done the kind of work that would be useful, and so I speculate.
You mentioned a few times about the redundancy of the structure. Are structures that are being built nowadays built to that same redundancy, or was it an unusual level of redundancy?
The amount of robustness and redundancy in structure is very dependent on where it's built. If you build it, and some of you are probably from Singapore, and in Singapore the wind hardly ever blows and the ground doesn't shake, and the structures are very light, and there's no great need for that kind of redundancy in the project. But those of you who come from the Bay Area or study seismic design, or you come from other areas where the wind loads are very strong, then of course you get more interested. in a building like the World Trade Center, if you imagine the Jolly Green Giant pushing the building laterally, and imagine that's a Los Angeles earthquake or a Tokyo earthquake, which is about the same. It takes about 5 Jolly Green Giants to account for the wind loads. So the wind loads are very much larger than the seismic loads. So, the design systems, however, are very different. Generally speaking, wind-resistant structures are designed to be elastic in the wind. Why? In Hong Kong, you get several typhoons a year, but you don't get several earthquakes in them. So it's kind of a different level of risk that goes with it. So it makes more sense, I think, to minimize structure damage and non-structure damage by designing inside of the elastic limit. Now, when we're looking at the 200 or 1,000-year event in wind-resistant design, then obviously we're expecting a lot of damage. Now, the Trade Center is an interesting design because the facade of the building is designed to come off before the structure comes in. That is, when the wind force gets up to a given level, then you're going to start losing glass and aluminum work, and that produces high level of aerodynamic damping, which stabilizes the structure and reduces the wind loads.
What's the tallest building you contemplated building?
The one that I showed you at the beginning is 500 meters high. It would be the tallest building in the world. Contemplated. Well, I mean, you can build a building to the moon. I mean, they're talking about the space elevator, right? You can do anything, particularly real estate. It takes a lot of money to build a very, very tall building.
How many basements does this building have? How was the excavation size maintained? And how did it affect buildings on the other side of the
Varied where you are, but 5, 6, 7 basements in the Trade Center. It's about, I'm terrible at numbers, it's about 1,800 feet long. The technique was used called a slurry wall system. Basically, you make an excavation in the earth, which is about 3 feet thick and some length, depends upon where you are. As you make the excavation, it's filled with a bentonite slurry. Bentonite is like a clay, very fine clay, and so it's kind of slippery in your fingers. And then the reinforcing bar cage is lowered into the bentonite and pipe put down concrete, and you've got a piece of wall, let's say it's 10, 20 feet long, 3 feet thick or 2 feet thick. And then you go along some distance away and do another one. And you come back and infill, so pretty soon you have a complete wall around. And that wall then goes down, in the case of the Trade Center, or most slurry walls, goes down into rock, or something akin to rock. And then excavation proceeds from the top down, and as you excavate away, then post-tension strands are put in, anchoring the wall back, to prevent it from buckling inside. And pretty soon you have an excavation, which is just a great huge hole with a concrete wall around it, and these tiebacks that would hold it in place. Now the trick is the tiebacks are carefully designed to provide a force which is equal to react to the wind, the earth and water load on the wall. So it's kind of in balance. And so the wall stays pretty straight. But when you actually build a basement, then it's quite elastic. It moves a lot. And in the case of the slurry wall, the trick is to design the slurry wall so that it's able to accept these deformations. Now the problem is the forces are big at the bottom and small at the top, but the technique is to allow the slurry wall to slope so that it maintains more or less straight. So it deforms more at the top than at the bottom, and that's done by analyzing the slabs to allow that motion. And it gets huge finite element analysis, multi-levels obviously, to make that possible.
But any damage across the building?
None.
We have a couple more questions.
Today's economy and political situation, what is the possibility? With today's economy and political situation, what is the possibility of removing the two towers, and is it possible that you have design ability?
What's going to happen on the side of the World Trade Center is the question. And there is a sort of committee which has been appointed by the governor and by the mayor, headed by a man named John Whitehead, who's a very brilliant guy, known pretty well. But I believe his thinking is in relatively modest type buildings. But in the words of famous Yankee catcher, you know, it isn't over till it's over. So we don't know what will actually go on the site. Hopefully, our community groups will have a lot to say about it. New York is run by very small little political groups, neighborhood groups, if you will, who decide what's built in their area. There's a lot of sympathy for building two very tall buildings. There's been a lot of people say we should build back what was there before. I think that would be a terrible thing to do. Absolutely terrible thing to do. Because, I mean, these buildings are 60 years old. 40 years old. 40 years old. But they're very old, and you know, we have moved along in life, and I don't think it's appropriate to try to replicate them.
A question of a slightly personal nature, not too rude, but as an engineer, I've actually stood and marveled at that building when it was up, and I wondered if you could divorce yourself from the sort of human tragedy of the event, what it feels like to have seen a project you spent so much time designing, and designing for failure on paper that you probably never expect to see. How do you absorb that, and what the personal sense of that was?
Well, actually, there's two aspects to the question. One of them is if you could ask me if I could divorce myself from the sort of personal side, and the answer is I can't. I never really have gotten very concerned about the loss of the buildings. I mean, they were important in my life, of course, but a lot of people died, some from the impact of the aircraft, some from the fire, some from the building falling on top of them. And when I first saw it, I saw it on television. I didn't know whether there was 1,000 or 25,000 people or 50,000 people in the project. And I never thought about the buildings. I just not able to do that. And would I do it differently? Of course I